So what you notice is that this matrix ends up with a very poor condition number, a very large condition number as n gets very large. And what that means is that eventually the columns of this matrix become approximately linearly dependent. Now, we set out to approximate our function f with a polynomial of degree n-1. And at the moment what we're saying is that we want to take a linear combination of the function 1 and then chi squared and so forth. And the problem is that those parent functions start looking very much the same on the interval 0 to 1. Well, what if we look for a different set of polynomials where we have a polynomial of degree 0, 1, 2, 3 and so forth, and we define that set of polynomials differently. Now, there's actually a recurrence relation between these different polynomials, but here I've just written out a couple of the first ones. And these particular polynomials are known as Legendre polynomials on the interval from 0 to 1. And they have the property that if you integrate the product of any two of these, then either you end up with 0 if you're not integrating the same two polynomials multiplied together, or some constant that depends on s if s is equal to t. In other words, if you integrate the square of the polynomial. That sort of kind of looks like an inner product, doesn't it? And it kind of looks like an orthogonality condition. So, what you can then do is do the exact same thing that we did before, which is create a matrix with as its columns the polynomial of degree 0 evaluated at chi0, chi1 and so forth, and then the polynomial with degree 1 evaluated at chi0, chi1 and so forth. And then multiplying that times the vector that now become the coefficients with which you take a linear combination of these columns, you would like for that to be approximately equal to phi 0 through phi m-1. Okay, now what's going on here? This here really is a sampling of the polynomial of degree 0. This is a sampling of the polynomial of degree 1 at points chi0, chi1 and so forth. Okay? The equivalent of this integration here, but now with these sampled polynomials, is to take the dot product of these columns. So, what we would hope is that this too is equal to 0 if s is not equal to t, and equal to 1 if s is equal to t. Well, not 1, but some constant. Now, it turns out that this isn't exactly 0 typically, but it ends up being approximately 0. And that's good enough. So, by picking the polynomials that we use as a basis for our approximation with an n-1st degree polynomial, we now create a linear system that has a matrix that has columns that are approximately mutually orthogonal. Not orthonormal, but orthogonal. And that translates into a matrix with a much better condition number.